Let's look at an example of rolling without slipping on an incline. We have a cylinder of mass capital M and radius capital R rolls without slipping down an inclined plane whose incline angle with the horizontal is theta. Determine first the acceleration of the cylinder's center of mass, and then second, the minimum coefficient of friction that will allow the cylinder to roll without slipping on the incline. And so in gray here, we have kind of the setup. We have our cylinder. The X marks the center of mass, and we see it is rolling as it goes down this hill. So we're going to start by drawing our free body diagram, because to figure out an acceleration, we need to know what forces are acting on our cylinder. And so we have the cylinder has mass M, so it has weight, capital Mg, acting straight down, and that vector is coming from the center of mass. Remember, weight always acts from the center of mass. The cylinder is on the surface, so there's a normal force from the incline onto the cylinder, and we know that's perpendicular to the incline itself. So here's our normal force. It also acts at the center of mass of the cylinder. And then, since it tells us that our object's rolling without slipping, that means there has to be a force causing our cylinder to rotate. Otherwise, with what we have right now, it's just moving translationally. And so rolling without slipping means we do have friction. And friction's a contact force. So friction, that force is actually happening at the contact point itself. So when we draw friction on our free body diagram, it's going to start at the contact point, so at the bottom of the cylinder here. And then we know it's pointing kind of up parallel to the ramp, causing it to, if it was just sliding, slow down. But since it's not a point mass, it can roll. It's causing it to roll. All right, so this is our force of friction. All right, and so when we look at which way the acceleration is in, we know that our object is accelerating down the ramp in the X direction. And so we're looking at the net force in the X direction, and we know that equals ma. And a is our translational acceleration, but that's what it's looking for, right? The acceleration of the center of mass. Well, the center of mass is just going to translate. So we are looking for that linear acceleration. Last little bit, there aren't any arrows directly pointing to the right, but we know we can break this weight vector up into components. I'll attempt to make a straighter line out of that one. Oh, not much better. But. So there's our right angle. When we break mg into components, remember the angle at the top here is equal to our angle theta. And so mg sine theta is the component down the ramp parallel to the incline. And mg cosine theta is the side, the vector component that is perpendicular to the incline in the y direction. All right, so when we sum up our net force in the x direction, let's call down the ramp positive. So we have mg sine theta minus the force of friction equals ma. I'm going to go ahead and make that a capital M because that's the mass of our cylinder. A little bit more we can do here. If you recall, friction was mu times the normal force. I guess I'll write it the same way. And looking at our free body diagram, there's not acceleration in the y direction, so the normal force is equal to the y component of the weight. So let's put that in. So mg sine theta minus mu times mg cosine theta equals ma. And we can do a little rearranging, just dividing everything by capital M. And we get A is g sine theta minus mu g cosine theta. All right, so we've made some progress on finding our acceleration, but at this moment, we don't know what mu is. So we're going to press pause right here. And luckily, we have another equation we can use for rotational motion, and we'll look at that in the next video.